Okay, I think we can start the lab.
Yes, sir.
Yes. So basically in today's lab we'll see things related to Fourier transform, and I hope that Rulami sir has already started teaching the Fourier transform, and maybe you have seen few equations and 1-2 problems. So today we'll try to see one example, one basic example of Fourier transform and how it is, how we can find out the Fourier transform of that rectangular signal, and then we'll see one property, and I have given as assignment, and few things will be shown here, and the rest of the things will be given as assignment. And also we'll learn Parseval's theorem. Maybe you have not heard this term Parseval's theorem, but we can discuss, and maybe very easy things. And also measurement of essential bandwidth, we'll try to cover this part. So if I start from the beginning, so Fourier transform is basically this is for continuous time non-periodic signal. So if we want to represent a time domain signal in frequency domain signal, and that signal is a continuous time non-periodic signal, then we use this Fourier transform. So by this time, I hope that you have seen these two equations. So in the previous class, I have said there is a Fourier series pair. Similarly, we have a Fourier transform pair. So x j omega, this is the representation in frequency domain. So we can, if we have xt, then we can calculate x j omega using this equation. And also if we have x j omega, we can go back to time domain. So basically we'll see one problem from the book. It is problem 3.25, and if you can see this is your first this is the topic where the continuous time non-periodic signal 3.7, that means the Fourier transform have started. So maybe the second problem that we have is the ft of a rectangular pulse. So this is the equation. That means it will be 1 for a particular period. That's why we are calling it as a rectangular pulse. So from minus t0 to t0, and so this is the visual representation of xt, and the corresponding x j omega has been calculated. So if I come here, so similar thing, just x j omega, this is the initial equation that we have seen how to calculate x j omega. So then we have replaced the limits from minus t0 to t0, and xt is equal to 1 in that limit, and otherwise it is basically 0. So if we integrate, then we will be here 2 by omega sine omega t0. So try to get this. So I'll be continuing this in the whiteboard. So try to get this equation is valid for omega not equal to 0. So we need to obviously calculate x j omega for omega equal to 0 also. So before going to that, let me ask that whether you have heard about the sinc function or not.
Yes, sir.
Okay, there is a we have the definite attributes of that sinc function. So basically let's start from here in the whiteboard. So if I draw the original signal, so it is from minus t0 to t0 is our xt, and we have t. So this t0, there is another variable, it is called tau. So basically tau is if we call the whole period for which it is 1, we call it tau. So tau is the relation between tau and twice 0 will be t0 will be 2 t0, and also t0 will be tau by 2. So basically your minus t0 in terms of tau is minus tau by 2, and here it will be tau by 2. Now if we have this is our xt, so we have x j omega, and after doing some calculation we have found that it will be twice 2 by omega and sine omega t0. Now from here, if we want that our if we want to declare this, or if we want to express this expression in terms of sinc function, then we already know that the sinc x, if we have sinc x, then it is sine, what is that, pi x by pi x. Okay. So now we need to express this sine omega t0 such that it falls within the this type of formula. So how can we do that thing? So we have sine, then we need a pi. So if we need a pi, then that pi will be divided here. So this part is basically your x here, sorry, in this part, and this is your pi. Then we need the same thing, pi omega t0 and pi. So here we can see we have previously we have omega here, so omega and omega will be there, but we do not have any t0. So basically will be 2 and t0 will be multiplied here. So now if we want to express in terms of sinc function, twice t0 sinc, then omega t0 by pi. Is it okay? Now if we want to express in terms of tau, then we have tau is equal to twice t0, so it will be tau sinc, and then omega tau by twice pi. So if we put t0 as tau by 2, then we'll be getting this equation. So now we have xj omega. So if we want to draw it like the figure in the book, then it will be something like this. So now if we want to find out these values, like if we want to draw this perfectly, then we need to have this amplitude and also this intersection points, isn't it? So how to find that thing? So basically it is omega axis. So we have said that this is omega not equal to 0. So at omega equal to 0, basically your xj omega will be need to calculate using the limit function. So if we use the limiting function in this particular case, we know that limit x sine x is whenever x tends to 0 is basically x. So from there we can say 2 by omega and omega t0. So this will be calculated, cancelled. So it is basically twice t0, or we can say tau. So this amplitude is basically, you can say twice t0 or tau. Is it okay? Is it okay up to this? One, you can just, yes, okay. So now if we want to calculate these intersection points, then how can we find that one? So at xj omega equal to 0, basically we need to calculate omega. So basically in these points your xj omega are 0. So how to find that thing? So this is your xj omega.
So the angle of sine should be plus minus n pi.
Yes. Angle of sine should be omega t0, and it should be plus minus n pi. So omega will be how much? Plus minus n pi by t0. So this point will be pi by t0, twice pi by t0, and here it will be minus pi by t0 minus twice pi by t0. So if we want to show in terms of tau, then it will be twice pi by tau. So if t0 has having this value, so basically it is twice pi by tau, is 4 pi by tau, and this is minus twice pi by tau, and obviously there is a reason for which I'm actually explaining these intersection points in detail. So that's it from this side. Now if we want to calculate x j omega, what are the things that we need? So using the sinc function, because we'll be calculating other things also. So if we want that x j omega in terms of sinc function, then what are the things that we need? We need to create a user-defined. We can create a user-defined function of sinc. So how can we create a user-defined function for this particular sinc function? So we'll see that thing in the coding. But so actually these things has been written here, the derivation parts, but I just explained so that things will be easier to you, and hopefully all of you have understood up to this. So this is the first code to have the sinc function here. So if I say this particular line is basically yi sine pi x by pi x, and we're dividing it element wise. Now I have just one question, that how we have defined these two lines, why we have written these two lines, what is the significant? Like if we have x, we could have directly written this particular line to calculate sinc function, isn't it? So why we have incorporated these two lines? There can be other ways, but in this code, can you explain these two lines? Anyone?
So to make it periodic.
Okay, can you unmute, keep yourself unmuted, because you need to explain a bit more, not a single line answer. Was it 34 or?
Sir, 88.
88. Alavi. So what was your explanation?
Sir, to make it a periodic.
To make it periodic, okay. So I'll be searching for other answers.
I can.
Sir, so that it doesn't.
Okay. One by one. 34. You
Sir, because sir, we need to find the command is find where x not is equals to 0. Because
yes.
if x becomes 0, then it will become undefined. So that's one of the use of the commands, which is I is equals to find x not equal to 0. And where the line is that y is equals to 1 size x, we need to create a matrix and the of ones which is incorporated with the size of the x.
Yes, that if that is the only purpose, then we could have used zeros. So can we use zeros there?
Sir, if
so what will be the values when x
Sir,
will be equal to 0?
I can,
yes.
Sir, for x equal to 0, this function is undefined. So for the elements for which x equal to 0, we need to define it in one way, and the elements for I defines the number elements. So for the elements for which n is not x is not equal to 0, in that case we will be able to apply this theorem.
Yes, so, yes. But whenever x equal to 0, what will be the value of y?
Sir, 2t0 by t.
2t0. Okay. If I go, we are only describing about the sinc function. So if we go
one.
Yes.
One, sir.
Yes.
One, sir.
It will be 1, because if we apply limiting function here, so it will be pi x by pi x, isn't it?
Yes, sir.
So at x equal to 0, basically your sinc function will be giving 1. Is it okay?
Yes, sir.
Yes. So you got the obviously you got the thing. So I will be considering. Then this is the case. Basically, we are declaring at the beginning. We're declaring all the elements to be 1, and then we're finding out the index for which x is not equal to 0, and only for those values of x we are calculating the value of y using this equation. That's how we have declared this one. So secondly, whenever we will be doing the here we have done a comparison. So just here you can see that x has been declared with two variables, omega and tau, and then tau sinc omega tau by twice pi. If you can remember, this was our x j omega. Now we have declared omega, and here during the plot we have omega in x-axis, then x omega is the function that has been supplied to it, and then this one refers to this tau. That means in the second case, this 0.5 is the tau, and third case, this 2 is the tau. So if we want to just visualize the thing, then we can find that, okay, our if this is our tau is equal to 1, then this is tau 0.5, this is basically tau 2. So you can see that the width of this this actually depends on this value of tau. So for these particular values, particular values, so what will be the corresponding xj omega? So we have seen that for tau is equal to, if we have tau is equal to 2, then in that case you can see our amplitude that we have calculated, it will be tau by 2. And tau, the intersection points, you can see tau is basically at the it is basically reciprocal, you can say, in a sense, like it is inversely related. That means if your tau is high, your the first intersection will be closer to 0 with respect to 0.5 and 1. So basically it is called the scaling property of Ft. Obviously there is equation related to this, but I have given one assignment at the end that you need to show that whether they are following the scaling property or not. In this case, you need to reproduce a figure and also try to show that the equation matches our scaling property is actually giving the same thing in this case. So if your rectangular pulse have tau is equal to 0.5, 1 and 2, in that case we are having the output like this. So in this case you can see tau is 2, tau is 1, tau is 0.5. So we are getting a narrower I should say spectrum in case of higher value of tau. So basically these are inversely related. And also we have xt as, here we have xt as our rectangular pulse in time domain, but also you will see that whenever the frequency spectrum of a signal is like rectangular, then corresponding time domain representation of that signal, you will see that is basically a sinc function. So sometimes we call it as a duality property, or you can find all these things in the later classes maybe. So I have also included that in the assignment. So is there anything that you want to ask up to this? Is there anything that you want to ask up to this? Okay, hopefully no. So then let's move to the next topic. We'll be discussing about the Parseval's theorem. So what we did, just we calculated xj omega using a particular equation. Sorry. We'll be using this equation to verify Parseval's theorem, and also in calculation of the measurement of essential bandwidth. We'll be talking about only one example for Fourier transform. So in this case, what is the statement of Parseval's theorem? The energy or power in a time domain representation of a signal is equal to the energy or power in the frequency domain representation. So basically for Fourier transform, the relationship, the signal is basically continuous time non-periodic signal. So we can say that non-periodic signal is basically having the energy signals, and the periodic signals are power signals. So if we rephrase this statement, then we can say that the energy in the time domain representation of a signal is equal to the energy in the frequency domain representation, and that has been normalized by twice pi. So basically Parseval's theorem is this holds for also Fourier series and other things, as the power is related here. So here two equations has been given. So first of all, try to get this thing very clear that we can calculate the energy using this equation separately, and also we can calculate the energy using this equation separately. And xt is the time domain representation, and x, okay, this should be x j omega. This should be your frequency domain representation of that particular signal. So I actually say normally to my students that this xt and xj omega t, these are the two representation of a single signal. Try to get. We are just visualizing this signal in two domain, in time domain and frequency domain. If we apply a low pass filter, or if we apply something here, that means you are applying on the same thing or not applying to the two different thing. So basically it is a representation xt and it is a representation in frequency domain. So what does it say? That the energy, if we the energy in the time domain representation of a signal is basically equal to the energy in the frequency domain but normalized by twice pi. So if we have that the particular signal unit amplitude pulse xt that we were discussing in the last example. So if we have a duration tau, then what will be the energy? So the energy has been calculated here. So basically it will be, limit will be from minus t0 to t0, and xt is basically 1. So if we just do few calculations, then you can see it is basically tau. That means we can say that for a unit amplitude rectangular pulse xt, the total energy will be equal to the total time for which it is basically 1. Is it okay up to this? Is it okay up to this?
Yes, sir.
Okay. So then we can write that this energy will be equal to the energy that has been calculated using the frequency domain representation, and that should be equal to tau. Now what we will do, so we know xt and we know what will be the total energy, and also we know xj omega. So whenever we put xj omega here, and we'll be calculating, we'll be integrating, or we'll be calculating this energy using this equation, then if that equals to tau, that means the Parseval's theorem will be verified. Obviously we'll be doing this in MATLAB. So that is the basic task, that we'll be doing this integration as we have the sinc function, and also we can calculate xj omega. So basically we can calculate this energy from this equation, and then we should verify that whether that is equal to tau or not. So if we go to the code, then you can see that this is the equation that we want to integrate. 1 by twice pi tau sinc omega tau by twice pi. That means 1 by twice pi, and that this part is your x j omega, and that has been squared. And now if we integrate this particular one, then we'll be getting the same equation that we are talking about, this equation. So now if I just I can give you just 1 or 2 minutes. You can see the documentation of integral. So how that has been used here, and what are the input arguments of integral. So I want to hear someone from your side. Okay. So let's pause for 1 minute. Okay. So what are the input arguments here for integral?
Sir, we give a function at the first place.
Yes.
Then we give the lower limit of the integration, and then we give the upper limit.
Yes. And what does this at the rate omega means basically in this case? Because our main function, we have two variables, isn't it?
So the main
Symbolic.
function we have x of j omega, so it's just
So we're integrating in terms of omega.
omega, sir.
Yes. We are integrating in terms of omega. And basically this one refers to this tau. So if you go for the documentation of integral, you will find that you can find that there can be one variable integration and also two variable integration. So we have followed if a equation have two variable, then how to solve that one. So here basically omega is the variable with respect to which we are doing the integration, and this one refers to this tau. That means after doing the running this code, so the answer that we'll be getting, that will be closer to 1, isn't it? And these two are the limit. So as we cannot give the in minus infinite and infinite in MATLAB, so we'll be giving a very small number and also a big number, so that we can have a closer value to 1. So if I just run this code here, so you can see this omega comma 4, that means we have 4 here as tau. So if I run this section, then you can see the answer will be closer to 4. So if we change this to, let's say 3, that means the thing that will be calculating, this is 2.999, that means it is closer to 3. So that's what we're trying to do, is to verify the Parseval theorem in using MATLAB. So there can be other way to do this particular thing. There is another function called quad, but maybe quad will be removed soon. So integral is the new command that will be given in the future. That will be only thing to integrate in future release. And also you can obviously you can do by yourself using other things. So the third topic that we want to discuss today is the essential bandwidth. So what is the essential bandwidth? So it says that the essential bandwidth is the portion of a signal spectrum in frequency domain. Try to get is the portion of the signal spectrum in frequency domain which contains most of the energy of the signal. So in this case, try to get that this definition have a issue with the most of the energy, because this most of the energy is not mathematically precise. So basically it will be, we need to define this, how much is the most of the energy. That means it can be, someone can say, okay, it is 90%, someone can 95%. So even if you go for finding out the definition of bandwidth, it depends on the application. So application to application, you can say the bandwidth is basically the signal spectrum in frequency domain, obviously. But how much of that one is the bandwidth? Because it can, let us say for this rectangular pulse, so we need the frequency domain from minus infinite to infinite. But for practical cases, what happens? We take a portion of it and say that, okay, this portion of this signal contains most of the energy, or it can represent the original signal a bit more or less. So this most of the energy. So what we'll do, we'll do the measurement of this essential bandwidth. So it will be a variable that how much energy we want from that signal, and then we'll calculate what will be the bandwidth for that particular percentage of energy of that signal. So if we say the E total for a signal if we want to calculate in the frequency domain, we get it from the Parseval's theorem so this is our equation. And if we want to find out the fraction of energy between minus W to W, then we can write this equation with the function variable W. So here from infinite to infinite, we have changed to minus W to W. And if we want that our energy will be a percentage of total energy, because if we want total energy, then we need the spectrum from minus infinite to infinite. But if we want that, okay, 90% of the energy of the signal, then what will be the bandwidth? Then we can solve this equation basically. So left hand side and right hand side is basically the alpha, that means the multiplying factor. Then we have E total. So basically we want to solve this one. We want to solve this equation in MATLAB, and we want to find out what is the value of this W. Is it okay? Is it okay up to this?
Yes, sir.
15 on 15.
Yes, sir.
So বুঝতেছো এখন পর্যন্ত বুঝতেছো তো না সহজ জিনিস. So how can we solve this one? So we'll be giving one code obviously. Thing is that for this lab I have added this assignment for this year, so I do not know how, whether if I hope that all of you can solve these very simple things. So basically I'm explaining everything in from the lab sheet so that you can give time to understand to do these assignments. And also the last date to submit the assignments will be 23rd of December. Okay, so here is the code. Let me show you the whole code. Can you see?
Yes, sir.
Okay. So let me take a screenshot from here. So I'll be giving you 2.5 or 3 minutes basically to understand the code, and I want someone to explain. Okay. Okay, I'm keeping this open. So is there anyone? Okay.
So I can try, sir.
Okay, 34, not you. Anyone else? Anyone else?
I can try.
Yes, 15.
Sir, I think I can try, sir.
Okay, let's go to 15. On 15.
Okay, sir. In the first line, we are taking the value of W.
So, okay, can you please repeat this portion, because even if it is written, but we need to know that what are the input arguments and what are the output arguments.
The input arguments ETT is equal to the total energy of the signal, alpha equal to the multiplying factor, and tolerance the tolerance we are accepting in the output.
Yes.
The W is the output argument. W is the essential bandwidth in radians per second. EW is the percentage of total energy.
Okay.
Now, at first we are taking W equal to 0 for initialization. Then we are taking the tau equal to E total, that is the input argument of our function, and we are taking the step initially to be 2 pi by tau.
So, is there any reason that for why you are taking twice pi by tau?
So I think that's the maximum in the main lobe. That's why. Sorry.
Yes, here it is twice pi by 2, isn't it? Twice pi by tau.
Yes, sir.
So from here to here.
Yes, sir.
Okay. Then
Now we are defining the x omega equal to the as the equation was, and it is a function of omega and tau, and then we know that
so this is the equation to calculate the energy without the integration part, isn't it?
Yes, sir.
Okay.
Now after that we are multiplying the total energy with alpha to get the energy that we need.
Desired or the energy that we want. Yes, the desired one.
Then the relative error is calculated as E minus 0 divided by E. E is the total, E was the total energy that we want. And
this is basically the initial relative error. So every time we'll be calculating in this loop, basically it is here relative error, but this is just the initial one. That initially, let us say our desired, this E is our desired one. So let us say initially it is basically 1. That's the thing. Okay, now go on.
Now we are we are running the loop while the absolute value of our relative error is greater than the tolerance level.
Yes.
So at first we are checking if the relative error is greater than 0. If it is greater than 0, then we are changing the value of W with W plus step.
Yes.
And if it is less than 0, we are changing the step value to half, and then we are reducing the W value to W minus W step.
Yes.
Then we are performing the integral to find the energy EW, and after that we are calculating the relative error by E minus EW by E. And
so basically EW has been calculated with the limit from minus W to W.
Yes, sir.
Isn't it?
Yes,
yes.
Sir.
That means we are following this equation. So from minus W to W, and we are calculating this whether there is that is equal to alpha E total or not, isn't it? Okay, then we will be moving around the loop
until the error is less than the tolerance level.
Yes. Whenever it will be equal or less than the tolerance level, it will terminate, isn't it?
Yes.
Now, just my question is in this if and else if. So, why we need to make the step down divide by 2 in this case?
Sir, can I answer?
Okay, let me come from 15 first, then 120 you can explain obviously. 15.
I'm not sure, sir.
Not sure. Okay. Then 120. You can go.
So we are checking the zero crossing of the j omega axis. So at the first zero crossing occurs at the tau value. So every time we are every time our relative error is not fulfilling our criteria, so we are the bandwidth w we are increasing. So if the relative error is greater than 0, that means we are at the right direction, at the positive axis. So we will be looking for the next zero crossing. So for the next zero crossing occurs at the tau by 2 value, sir. Every time the next zero value will occur at we need to find the next zero crossing value we need to divide it by 2, sir.
Okay, yeah. Oh, okay. So basically, you are saying that whether we are finding out this zero crossing or not, isn't it?
Yes, sir.
Okay. So let me discuss this thing. Obviously, thing is that these two step size are not the same. That is the main thing, isn't it? The two step size, whenever we'll be going forward and backward, these two are not same. That is the main thing. So why those two are not same? So first of all, try to get that whenever we'll be let us say our desired omega or w, sorry, I'm calling that as w. So this is minus w and this is w. Let us say we want that our value, it can be anywhere in omega axis. So let us say this is our desired w, for which we have 90% of the energy. Now at the beginning, what we have said at the first part of this code, we have the relative error is equal to 1, which is greater than 0. That means our first step will be here, isn't it?
Yes, sir.
So it will be, so let us say w1 and minus w1. So if we calculate EW1, basically in this particular case, what will be our relative error? Will it be greater or less than 0? So
it will be less, sir.
It will be less than it will be
EW.
No, it will be greater than 0 because you have E minus basically EW and then divided by B. So it is basically we're doing this as negative. So basically relative error will be greater than 0. So again we'll be adding the step size. That means now we are in this zero crossing, twice pi by tau. Then another step will be added, that is twice pi by tau. That means it will give 4 pi by tau. So we will be coming here. So now let me use another marker. So let us say this is your W2 and W2. So if we have EW2, so in this particular case, what will be your relative error? So using this equation, will it be greater or less than 0? 120?
Sir, it will be less than 0, sir. Because
it will be less than 0.
It is more than the desired.
Yes, it is more than the desired bandwidth, and also whenever we'll be calculating the energy, it will be more than the desired one. So now, if we do the same thing, that okay, we write okay only this particular line W minus step, then what will happen? So we'll be getting same thing, twice pi by tau. So we'll be jumping to here again. Then again we'll be getting relative energy greater than 0. Then we'll be jumping here. So it will be just in these 2 points. So for that reason, basically we are subtracting this step but divided by 2. That means next time it will jump to here. Then again it will calculate and then it will find it is greater than 0. Then it will jump to there. And then in the next step it will be greater, then it will be jumping here. And after some time you can find that your relative error will be 0 and you'll be getting the this particular minus W and W. Is it clear to you all? Is it clear to you? 15?
Yes, sir.
And 120?
Yes, sir. Clear.
Yes. So that is the thing that has been used. That is the I should say algorithm that has been used to calculate to find the essential bandwidth that has a percentage of the total energy. So if I go to run this particular portion, so in this case our tau is 2 and the total energy, and also we can call it tau in rectangular pulse signal, and then we want that 90% of the energy, and the tolerance level has been given as 0.001. So if we run this section, then you will find that the essential bandwidth W, that means the 90% of the energy resides within 2.6507. And finally we get this, okay, this is basically the 90% or close to 90% of the total energy. So that's all from actually my side. Is a obviously very small and easier lab. So I hope that you can solve these assignments and can submit within 23rd of this month. And let me take the attendance, and by this time if you have any question then you can ask after that. Okay. So from section A2 I'm starting with 11.
Present, sir.
Okay, then 29. 29. দেখতেছি তো 29.
Sir, 29 present, sir.
Yes, yes. Then 38.
Yes, sir.
Okay, 40.
Yes, sir.
41.
Yes, sir.
And 42.
Yes, sir.
Okay, 43.
Present, sir.
And 44.
Yes, sir.
44, okay. 45.
Yes, sir.
46. 46.
Yes, sir.
Okay.
Yes, sir.
52.
Yes, sir.
66.
Present, sir.
And 71.
Present, sir.
81.
Present, sir.
94.
Yes, sir.
107.
Yes, sir.
Okay. Then 11.
Yes, sir.
120, 126. 126. 9. Okay, then 139.
Yes, sir.
142.
Yes, sir. 130, sir. 126, sir.
126. Okay. Then 146.
Yes, sir.
147. 147. I say 9. 148.
Present, sir.
Okay, 153.
Yes, sir.
154.
Present, sir.
156. 156.
Sir, 156 present, sir.
Okay. Then 160. 160. I say 9. So let me announce the absentee list. 147 and 160. 147.
Sir, 155 present, sir.
155 তো কোন সেকশনে?
Sir, B2.
হ্যাঁ, B2 তে এখনো যাই নাই আমি। বুঝতে পারছো? Okay, now from B2, 35. 16 plus 35. Yes. Then 147, 9, 09.
Yes, sir.
Sir, 147, sir.
16 batch.
Sir, 17 best, sir. A2.
Okay, A2, 147. Okay. Then 169. তাহলে A2 থেকে. Okay. Then 13.
Yes, sir.
Okay, 16.
Yes, sir.
33.
Yes, sir.
34.
Yes, sir.
Then 48. 48. 9. 88. Okay,
Yes, sir. 88.
89.
Sir, 88 present, sir.
Yes, yes, 88.
Yes,
present.
sir.
Then 91.
Yes, sir.
92. 92. 9. I say.
Yes,
Okay, okay. 92 present. 92 present. 90, 93.
Present, sir.
Okay, 98.
Yes, sir.
99.
Yes, sir.
Okay. Ashikur Rahman. Then 103.
Yes, sir.
109.
Yes, sir.
115, 15 present. 18.
Present, sir.
And 134.
Yes, sir.
141.
Yes, sir.
144.
Present, sir.
44. And 145.
Yes, sir.
149.
Yes, sir.
And 155.
Yes, sir.
179. 179. 179. So those who are absent from section B2, 179 and 48.
Sir, I'm from B1. I couldn't join the morning class today.
What's your ID?
Sir, 53.
53.
Sir, I'm also from B1, 57.
57. Yes, I have
Sir,
given.
I'm from A1.
Sorry.
Okay, one by one. One by one.
Sir, B1 53.
B1 53. Okay, 57. Okay, then
Yes, sir.
86 B1.
86.
Yes, sir.
Okay, then
Sir, is
Knowledge.
150? Sir, have you given 156 present, sir, from A2?
156.
Yes, sir.
Yes.
Sir,
I have given.
I was lagging in grade. Thank you, sir.
Sir, 15 from A1.
15 from A1. Yes, I have given.
18 from A1.
Yes, I have given that one also. Okay. That's all from my side. Thank you.
Sir, I have one question.
Yes.
Sir, can you give us some suggestions about the lab quiz?
Of 4602.
Yes, sir.
Okay, so about this part, I should say, okay, we have not prepared the question yet. That's the first thing, and second is that we will be taking the online quiz for the first time this year. So obviously we need to think, but there you'll be having short questions, not long, but that will be written, and we have decided that will be written. And you'll be giving handwritten quiz, and also you need to upload that making PDF. So you will be getting short questions, like you need to explain something, or you need to write few. It may happen that you need to write a few lines of codes, or you need to. These are the things just related to the lab sheet. Is it okay? 57.
Yes, sir.
Okay, thank you for being here. Salam.